That was a long night. Death Stranding 2 just dropped and I played all night. Now, the coffee would be perfect. Sitting there, tired but oddly motivated, I watched the water as it started to boil. It didn't take long, but for me, it felt like forever. Not just because I was waiting for the coffee, but because the process itself somehow fascinated me. Because what we are looking at is a controlled mini catastrophe. Billions of water molecules suddenly starting to move chaotically. Faster and faster until they explode. Well, evaporate. Heat is a weird thing. A gas full of movement is hot, but if it's moving slowly, it's cold. The warmer it gets, the faster it moves. Man, the sun must be the ultimate heat. So unimaginably hot. Surely nothing can top that. Or can it? What if I told you heat isn't just a sensation but a weapon? A principle that can tear matter apart. Not just a little, but down to the deepest layers of reality. What if I told you there is a point where heat no longer just heats things, but melts space and time itself? And what if I told you that this was just the beginning of everything? The Big Bang wasn't an explosion in the classical sense. It was a state of maximal temperature, maximal energy density. A moment when the universe itself was so hot that it couldn't stay stable. It had to expand. That means if you concentrated enough energy into a tiny space today, you could theoretically do the same thing. You could create another universe. So today's question is a special one. How hot can it actually get? And what happens if you go too far? Heat might sound like something purely subjective at first. We feel warmth, soup boils, fire burns. But in physics, heat is nothing more than motion. More precisely, the average kinetic energy of particles. Gas is hot when its molecules move quickly. The faster they go, the hotter it gets. That also means that the temperature absolute zero means no movement at all. Motion is energy, and energy is temperature. Which is quite simple, right? But, motion has consequences. Because if particles move too fast, they can no longer hold together. Molecules break apart, atoms lose their electrons, and even the building blocks of atomic nuclei. Protons and neutrons, they start to dissolve. And eventually, all that remains is raw, unbound material. So quarks, gluons, and naked energy. And this is not some, exotic phenomenon. It's a fundamental property of reality. Heat isn't just warm or unpleasant to someone. It's kind of a universal solvent for structure. And that's why it matters, because more energy you put into a system, the more it tears apart. It sounds dramatic, but it goes even further. What happens when you push this principle to the limits? What if pure energy is enough to rip the universe apart? If heat is motion, then temperature is a measure of chaos. The hotter it gets, the more structure breaks down. And we can pinpoint this process surprisingly well. At around 10,000 degrees Celsius, atoms start losing their electrons. This is a state known as plasma, the fourth state of matter. Sounds like science fiction, but it's everyday stuff. Fluorescent lights, lightning bolts, and the surface of the sun, they all contain plasma. Speaking of the sun, its surface sits around 5,500 degrees Celsius, but its core exceeds 15 million. And even that is actually nothing compared to, supernovas. In the core of a collapsing star, or during the collision of neutron stars, temperatures can exceed 1 billion degrees. These conditions are so extreme that even atomic nuclei fall apart. And in particle accelerators here on Earth, like the one at CERN, we've managed to recreate conditions so extreme that even protons and neutrons break down. Their components quarks and gluons, become so hot and energetic that they form a new state of matter. This is the quark-gluon plasma. It kind of reflects the universe, or what the universe looked like just microseconds after the Big Bang. At this point, temperature isn't just a property of matter, it becomes a force that destroys matter. And yet, even these insane temperatures are just the beginning. There is a physical limit, a temperature so high that space and time themselves begin to collapse. Classically, if you keep pumping energy into a system, it keeps getting hotter. But there is a point where this logic breaks down. This is the Planck temperature. This temperature is so high that it's a 1 followed by 32 zeros. This isn't just very hot. This is the temperature at which our fundamental physics theories start to collide with each other. Why? Well, because temperature is ultimately just energy per particle. And I will be mentioning that a lot during this video, so be prepared. So, if you cram enough energy into a tiny region, say a space with the radius of the Planck length, so an unimaginably small region of space, something extreme happens. The energy density becomes so high that space-time itself starts to bend and twist. According to Einstein's general relativity, any form of energy curves space. Normally isn't a word, I'm so sorry for my accent. Normally, that's fine. A star bends space-time a bit, a black hole a lot. But at the Planck temperature, the curvature becomes so extreme that space doesn't just bend, it destabilizes. The very laws of classical physics break down at this point. And this is the point where two great theories clash. General relativity describes gravity as a property of spacetime, and quantum field theory describes particles and forces as waves in fields. Each works beautifully on its own, but they do have a problem. They contradict each other when energy becomes this concentrated. The Planck temperature is exactly that collision point. We have no reliable theory to describe what happens there, no theory of quantum gravity that can unify both realms. But we do know this: at this temperature, all matter breaks apart. No particles, no structures, no stable states, only raw and naked energy, gravity, and a space-time that begins to churn like a boiling foam. Physicists call this quantum foam, a picture of space-time fluctuating wildly at the tiniest scales. In theory, this chaos could even produce an event horizon, as if that tiny hot region turns into a microscopic black hole. Or even stranger, it could turn into a whole new region of space, disconnected from ours. This is what physicists call a baby universe. These ideas sounds really wild, but they are based on real mathematics. And it's also important to mention, we are not talking about lab conditions here. The hottest temperatures ever achieved in experiments like the quark-gluon plasma at CERN are around 4 trillion Kelvin. That's still 28 orders of magnitude below the Planck temperature. We're nowhere near that threshold, but it defends the horizon of what we even can think in physics. So what if, somehow, we could actually reach it? Well, what if we could heat a tiny region of space up to the Planck temperature, and in doing so recreate the very conditions that once created the universe? Up until now, we talked about heat as motion, as energy, as a force that dissembles matter. But now we're stepping into a new territory, because beyond a certain point, heat is no longer just a property of matter. It becomes a property of space itself. And if you go too far, space-time can collapse or form something new. The key word that we are looking for right now is energy density. Not just energy, but how much of it is packed into a little, really small space. Now, imagine stuffing so much energy that, for example, a supernova can ever produce, into a space smaller than a proton. At that point, space-time becomes soft. It becomes like butter. Because according to Einstein, energy curves space-time. The more energy you can cram into a small volume, the more intense the curvature. This happens in stars, in neutron stars, and most of all, in black holes. If the energy density exceeds a critical threshold, an event horizon forms. Space-time curves so violently that nothing can escape, not even light. And you heard that sentence probably 100 times. But what if you don't create a black hole? What if you create something else? Some models in theoretical physics suggest that a region of extremely high energy density could create something like a vacuum bubble. So a patch of space that doesn't fit into our own bubble, into our own universe, because it follows a different physical rule, a different energy density, and a different geometry, a different kind of space-time. This bubble could pinch off from our universe. It could, like an unstable particle, tunnel into a new state. And the new state would be, well, its own space-time, a brand new universe. This idea is called a baby universe, a region of space-time that separates from our own reality and begins to expand independently. From outside observers, it's hidden, like a black hole. For observers inside, it's a whole new cosmos, with its own beginning, its own timeline. And what does it all have to do with heat? Well, everything, because temperature is energy, and energy curves space-time. If you heat a system so intensely, compress it so violently, that you reach the Planck density, then it's no longer physically possible to contain that energy within our own space-time. The structure itself breaks down. And from that breakdown, according to a theory, a new universe could emerge. So, could we actually build something like that? In theory, yes. In practice, no. I'm sorry to, disappoint you. The amount of energy needed and the compression required in space-time are far beyond anything we could ever achieve. But the theory itself is solid enough that many physicists take it seriously. Some even believe maybe black holes aren't the end, but the beginning. Maybe every black hole is the seed of a new universe. And that would mean our own universe was maybe someone else's mini Big Bang. So, could this really happen? Could it already be happening inside black holes? And what does it tell us about the origin of our own universe? Maybe our beginning wasn't the start of everything, but the collapse of something else. And if so, what does it say about the end? When we think of the Big Bang, we often imagine an explosion, a massive Big Bang that brought space and time into existence. But that's a metaphor, and it is misleading. The Big Bang wasn't an explosion in the usual sense. There was no center, no shockwave, no surrounding medium that got torn apart. But what it was a state of maximal energy density, a moment of unimaginable temperature. You could say the Big Bang wasn't loud, it wasn't an explosion, but it was hot, and that's the key. Right after the Big Bang, the universe wasn't an empty space waiting to be filled. It was a space of density, a boiling soup of energy, quantum fluctuations, radiation, and the potential for all particles and forces we know today. So, matter we see today, like galaxies, stars, and atoms, didn't even exist as a possibility. It was pure energy plasma, which makes heat not just a side effect, it was the main actor. But then why did the universe expand? Well, precisely because of the heat. Because a state that hot and that dense is unstable. Again, for the 100th time, energy curves space-time, and if the curvature gets too strong, space can't stay static. It has to expand to become more stable. In a way, the expansion of the universe was kind of a thermal safety valve, a release outward. But that's not all. Immediately after this initial phase came something strange. The so-called cosmic inflation. Inflation was a super short, super fast expansion of the universe, faster than light even, but still allowed by physics, because it wasn't just matter that was moving, it was space itself that was stretching. What does it have to do with heat then? Well, before inflation the universe was tiny, but insanely hot. In a tiny fraction of a second, it expanded by a huge factor, cooling down dramatically. But after inflation, that condensed energy was released again in a process called reheating. That's when the universe heated up again, this time giving rise to particles, atoms, stars, and galaxies we see today. Heat was the unifying thread, first destructive, then creative, first pressure, then unfolding, first chaos, then structure. Some theories go even further. Yeah, I don't think further is a word. They go even farther. Farther? Well, now I lost my case. I'm sorry. So, in entropy cosmology, for example, it's proposed that the origin of the universe wasn't particles or fields, but information and entropy. In other words, the increase of a disorder, the thermodynamic gradient, wasn't the result of a Big Bang, but its cause. If that's true, then heat, understood as motion, energy distribution, and entropy, wasn't just a byproduct of the universe's birth, it was its very trigger. So, my question at the end, can I make coffee? I think so. And thank you for watching, by the way. This is a video that I posted first on my German Entropy channel, and now I wanted to go to do a little bit more and go international. So I hope you really like it. It will take some time to get used to speaking, in English and pronouncing words, but I will get to this point. So thank you very much for watching, and I hope to see you in the next video.